So now we have seen that controls deals with dynamical systems in generality, and robotics is one facet of this. Now, what we haven't done is actually try to make any sense of what this means in any precise or mathematical way. And one thing that we're going to need in order to do this is come up with models. And models are going to be an approximation and an abstraction of what the actual system is doing, and the control design is going to be made or done relative to that model and then deployed on the real system. But without models, we can't really do much in terms of control design. We would just be stabbing in the dark without knowing really what's going on. So models are actually key when it comes to designing controllers. Because if you remember, the question is really how, in control theory, is how do we pick the input signal U? So U, again, takes the reference, compares it to the output, the measurement, and comes up with a corresponding course correction to what the system is doing. And the objectives, when you pick this kind of control input, well, there are a number of different kinds of objectives. The first one is always stability. Stability, loosely speaking, means that the system doesn't blow up. So if you design a controller that makes the system go unstable, then no other objectives matter because you have failed. Your robots drive into walls, or your aerial robots fall to the ground. Basically, stability is always control objective number one. Now, once you have that, the system doesn't blow up. You may want it to do something more than just not blow up. And something that we're going to deal with is tracking a lot, which means here is a reference, either a value, 14, how do we make our system do 14? Or here's a path, how do I make my robot follow this path? Or how do I make my autonomous self-driving car follow a road? So tracking reference signals is another kind of objective. A third important type of objective is robustness, in the sense that since we are dealing with models when we're doing our design, and models are never going to be perfect, we can't overcommit to a particular model, and we can't have our controller be too highly dependent on what the particular parameters in the model are. So what we need to do is design controllers that are somewhat immune to variations across parameters in the model, for instance. So this is very important. I'm calling it robustness. A companion to robustness, in fact, one can argue that it's an aspect of robustness, is disturbance rejection, because at the end of the day, we are going to be acting on measurements, and sensors have measurement noise. Things always happen. If you're flying a quadrotor in the air, all of a sudden you get a wind gust. Now that's a disturbance. If you're driving a robot, all of a sudden you're going from linoleum floor to carpet, now the friction changed. So all of a sudden you have these disturbances that enter into the system, and your controllers have to be able to overcome them, at least reasonable disturbances for the controllers to be effective. Now once you have that, we can wrap other questions around it, like optimality, which is not only how do we do something, but how do we do it in the best possible way. And best can mean many different things. It could mean, how do I drive from point A to point B as quickly as possible, or using as little fuel as possible, or while staying as centered into the middle of the road as possible. So optimality can mean different things, and this is typically something we can do on top of all these other things. And in order to do any of this, we really need a model to be effective. So effective control strategies rely on predictive models, because without them, we have no way of knowing what our control actions are actually going to do. So what do these models look like? Let's start in discrete time. This means that what's happening is that at distinct time instances, things happen. In discrete time, what we have typically is that the state of the system, remember that x is the state, so this is at time instance k plus 1. Well, it's some function of what the state was like yesterday at time k and what I did yesterday. So the position of the robot tomorrow is a function of where the robot is today and what I did today. And then f somehow tells me how to go from today's state and control input to tomorrow's state. This is known as a difference equation because it tells you the difference between different values across different time instances. So that's in discrete time. And here's an example of this. This is the world's simplest discrete time system. It's a clock or a calendar. This is the time today. Now I'm adding 1 second, and this is the time 1 second later. So the time right now plus 1 second is the time 1 second later. This is clearly a completely trivial discrete time system, but it is a difference equation. It's a clock. So if we plot this, we see that here is the state, which is what time it is, as a function of time. So it's silly, but at 1 o'clock, the state is 1. At 2 o'clock, the state is 2, and so forth. And you get this thing with slope 1. So this would be the world's simplest model. There are no control signals or anything in there, but at least it is a dynamic, discrete time model that describes how a clock would work. Now, the problem we have with this, though, is that the laws of physics are all in continuous time. And when we're controlling robots, we are going to have to deal with the laws of physics. Newton is going to tell us that the force is equal to the mass times the acceleration. Or if we're doing circuits, Kirchhoff's laws is going to relate various properties to capacitances and resistances in the circuit. So we're going to have to deal with things in continuous time. And in continuous time, there is no notion of next. But we have something almost better, and that's the notion of a derivative, which is, it's not next, but it tells us how is the time change, the change with respect to time. So in continuous time, we don't have difference equations. What we have are these things called differential equations. And right here, you see that the derivative of the state with respect to time is some function of x and u. So this is not telling me what the next value it is. It's telling me what's the change, instantaneous change. And here is the same thing, but now I've written x dot instead of dx dt. And time derivatives, a lot of times, is written with a dot, and I'm going to use that in this class. And this actually traces back to the slight controversy between Newton and Leibniz. So in 1684, Newton said, oh, I have this idea that I call it differential, and Leibniz at the same time had the same idea. Well, this is Leibniz notation, and this is Newton's notation. And we're going to use the dot for time derivatives here. The point is that these are both the same equations, and they are differential equations because they are relating changes to the values of the states. So if we go back to our clock, what would the differential equation of a clock look like? Well, it would be very, very simple. It would say that the change, the rate of change of the time is 1, which basically means that the clock changes a second every second. That's what it means. So when I drew this picture of the discrete time clock, or I drew this line diagonally across it, what I was really doing was describing this. So this is the continuous time clock. X dot is equal to 1. And we are going to need, almost always, continuous time models for our systems. And next couple of lectures, we're going to start developing models of particular systems. But before we do this, I want to say a few words about how to go from continuous time to discrete time. Because our models are going to be continuous time differential equations. But then when we're putting this on a robot, we're going to put it on a computer. The computer runs in discrete time. So somehow we need to map continuous time models onto discrete time models. So now if I say that x at time k, well, it's x at time k times delta t, where delta t is some sample time. So we've sampled k measurements. Well, if I use this, what is x at time k plus 1, which is at the k plus first sample time? Well, I need to relate this thing somehow to the differential equation. So how do I do this? Well, this is not always easy to do exactly, but what you can note is that this is known as a Taylor approximation. So x at the time k times delta t plus a little delta t, which is exactly the next state. Well, it's roughly what it was last time, times the length of the time interval, delta t, times the derivative. So this is an approximation, but the cool thing here is that this x at time k plus delta t, well, that's xk. So these things are the same. X dot at time k plus delta t, well, that's f. So these are the same things. And then I just have to multiply my delta t there. So this is a way of getting a discrete time model from the continuous time model. And this is how we're going to have to take the things we do in continuous time and map it onto the actual implementations on computers that ultimately run in discrete time.